All right, so last lecture we were talking about an introduction to the gas laws. And so today we're actually going to start looking at the mathematical formulas that show the relationship between our four variables: pressure, volume, number of moles, and temperature. All right, so our first one is called Boyle's law. And Boyle's law relates pressure and volume. So we're saying that the other variables would be constant. We would not have a change in temperature or number of moles. Only the pressure and volume would be changing. So if the temperature stays the same, as the pressure increases, the volume decreases. And this is called an inverse relationship, meaning as one goes up, the other goes down. So they sort of go in opposite directions. And so our formula is P1 times V1 equals P2 times V2. So we have a gas with a volume of 3.10 liters. I identify that as a V1, volume 1, and it has a pressure of 1.30 atmospheres. So this is a P1. It is placed into a new container with a pressure of 1.6 atm. So this is a P2, a new pressure. What is the new volume? V2. So now that we've identified our variables, what we want to do is manipulate our formula so that we're solving for V2. So if I come over here, if I divide both sides by P2, then I would be solving for V2. So my new formula is going to look like this. V2 would be equal to P1 times V1 over P2. So now we just plug in our numbers. And I like to include the units when I do this because if you include your units, you will be able to see what cancels and what units our answer will be in. And this will also kind of back you up that you're setting it up correctly. So my P1, 1.30 atm times my V1, which was 3.10 liters. And then I'm going to divide by P2, which was 1.60 atm. And when you work that out, you are going to get an answer of 2.52 liters. Notice ATM cancel, so I know my answer will be in liters. And for sig figs, so we're big on sig figs in chemistry, you know that. And so when you're rounding, you're going to look at all your original numbers. And the rule for multiplication and division is that you're going to round to the least number of sig figs. Now in this case, all three of my numbers have 3, so my answer can also have 3. So 2.52 liters would be my answer. Here's a little diagram of, here we go, of Boyle's law, an animation. So notice what we're doing here is we're increasing the pressure, and as the pressure increases, the volume, or the amount of space the gas takes up, it decreases. And notice that the temperature is staying constant. This is also so that you can see in real life. So if I suck the air out of a container and I create what's called a vacuum, I lower the pressure. So the pressure is decreasing, and it's really interesting to look at with something like pipes that are full of little holes. As the volume, as the pressure decreases, notice how the volume, the amount of space that the pipes take up, it increases. And the same thing on the right here with a balloon. As I decrease the pressure around the balloon, the gas basically spreads out. All right, Charles's law relates temperature and volume. So if the pressure doesn't change, temperature increases, the volume also increases. So temperature and volume are directly proportional to one another. And for this one, the temperature would have to be in Kelvin. So that's really important. You cannot use Celsius temperatures for this because Kelvin is directly proportional to kinetic energy. But with Celsius, because you have 0 in the middle there, because it's based on water, and you also have negative numbers, it would throw everything off. Your answers won't be accurate. So you have to convert to Kelvin if they give you Celsius. So let's take a look at this one. A gas sample has a volume of 8.57 liters at 273 Kelvin. So this one's already in Kelvin. That's good news. So we have a V1, we have a T1, and then we have a what will the volume be? So we're looking for V2, and we have a T2. Now, because this one is a fraction, and this is really important, people mess these up a lot. My recommendation to solve these so that you don't make mistakes is cross multiply. V1 times T2 will be equal to V2 times T1. And now, since we're solving for V2, we'll just divide both sides by T1. T1 will cancel, and then we would be solving for V2. So my final formula is going to be V1 over T2 over T1 will be equal to V2. I highly recommend that you manipulate the formula before you plug in numbers, because so many times people will plug in numbers, and particularly with the ones that are fractions, and they end up multiplying when they should divide, or divide when they should multiply. So if you cross multiply the formula and then divide by the one, manipulate it so that you're dividing, you'll have it correct every time. All right, so plugging in numbers, again, this is basic algebra. We're just going to plug in our V1, 8.57 liters, times T2, which is 355 Kelvin. We're going to divide that by T1, which is 273 Kelvin. Notice that Kelvin will cancel, and our answer will be in liters. And rounding this to 3 significant digits, because all of our numbers have 3, is going to be 11.1 liters. Here is a diagram of Charles's law, kind of showing you how, again, in this case, we're not changing the pressure, right? You have 2 weights, and the 2 weights stay the same, but we're increasing the temperature, and the volume of the gas increases. All right, Avogadro's law. So we're not actually going to test you on this one, but first of all, equal volumes of gases at the same temperature and pressure will have the same number of particles. So this one relates moles. So any gas, just FYI, at STP, that's standard temperature and pressure, will occupy 22.4 liters and would have exactly 6.02 times 10 to the 23rd particles. So just a reminder, standard temperature and pressure, 1 atmosphere is standard pressure, or 101.3 kPa, or any of the other units we talked about. And standard temperature is 273 Kelvin, which is the same thing as 0 Celsius, because Celsius plus 273 gives us Kelvin. So this one would be V1 over N1 equals V2 over N2. Again, you do not have to do this one on the test. We're not going to include this one on the test. So I'll just give you the answer, but you're welcome to try it on your own. So remember, I recommend for these problems, so V2 over N2, I would cross multiply and get V1 N2 equals V2 N1. And then you just figure out which variable you're solving for and isolate that one. If you work this one out, you will get 11.9 liters. You would be looking for V2 in this problem. But again, I'm not going to work it since this particular formula is not going to be on your test. All right, Gay-Lussac's law is going to be on your test. So Gay-Lussac's law, again, these get very repetitive, as you can see, says that as temperature increases, pressure also increases. So this is also a direct relationship. We're assuming for this law that the volume stays the same. And so here's a sample problem. So P1 over T1 equals P2 over T2. If we cross multiply, we're going to get P1 T2 equals P2 T1. And then we can isolate the one we're looking for. So let's take a look. So we have a pressure of 103 kPa. So this is a P1. At 25 Celsius, this is a T1. But be careful on this one. We need to change it to Kelvin. So to change to Kelvin, you add 273 to your Celsius temperature, which would make this 298 Kelvin. If you use Celsius, you will get the wrong answer. So make sure that you change to Kelvin. The can is thrown into a fire. What will the new pressure be if the temperature is raised to 928 Celsius? So we are looking for P2, and they are giving us a T2. Our T2, again, needs to get changed to Kelvin. So if I add 273 to that, all right, and I'm going to get 1,201 Kelvin. And now that I've manipulated my formula, I'm going to go ahead and plug in my numbers. Sorry, my pen is not working here. Okay, so sorry, so let me manipulate my formula. Sorry, let's see. Okay, so we said we are looking for a P2. So we're going to divide both sides by T1. And then that would solve for P2. And now, again, we're just going to plug in our numbers. So P1 was 103 kPa. T2 is going to be 1201 Kelvin. T1 is going to be 298 Kelvin. Our kelvins will cancel. Our answer will be in kPa. We're going to round to 3 significant digits. I know 25 has 2 significant digits, but when we change it to Kelvin, since adding, we go to the same decimal place. That's the rule for adding. So basically, once we turn this to a Kelvin temperature, it has 3 significant digits. So 415 Kelvin, kilopascals, kPa would be our answer. All right, so that's Gay-Lussac's law, and again, here's what happens with this one. So now, see, notice this, the volume can't change. The volume, remember, is the size of our container. So this is a rigid container, so when I heat it, the pressure increases. In other words, these are hitting harder and making pressure, but the volume doesn't change. I mean, unless this failed and the container exploded, which theoretically could happen if you got it hot enough, probably not in this experiment. And then if I cool it, the pressure drops. So if the volume is steady, if it's a balloon, the volume can change, right? A balloon can increase in volume. It can get bigger or it can get smaller. But a rigid container, the volume is going to stay the same. All right. Last one for this lecture, and then we'll go into the last couple of gas laws in our next lecture. So combined gas law actually combines all the ones we've learned so far. So if we don't include moles, and this is actually the one that'll be on your test. So if we can do P1 V1 over T1 equals P2 V2 over T2. So we can actually put all the gas laws together. And notice, oh, sorry, there's another version of this, which we won't be using on the test, but P1 times V1 over N1T1, if we include moles, is equal to P2 V2 over N2T2. So we won't be including the moles on the test, but that is another version of this. So here's the cool thing. If you can just remember this one, you could plug in your numbers, and if you realize, hey, you know what? The number of moles and the temperature didn't change. Oh, okay. Well, if those things didn't change, cross them out, and look what we have. We're back to Boyle's law. You know, or if you're doing it and you notice the pressure doesn't change, or you notice the temperature doesn't change. So you can actually get all of the other gas laws. Look, if volume doesn't change, cross it out. And what do we have? Gay-Lussac's law. So pretty much all this is, that's why it's called the combined gas law. It literally combines the gas laws. And so we could take this one and solve it. Again, I would recommend you cross multiply, so you would get P1 V1 T2 equals P2 V2 T1. So like for this one, we have a V1, we have a T1, we have a P1. They are asking for V2, and they're saying to do it at STP. So they have it, this is our T2, and this is our P2. So we would be solving for V2. So what we would do is we would basically divide by P2 and T1. Cross these out. P2, T1. These would cancel. And to get V2, this would be our formula. And then we would just plug in our numbers. We'd put in our P1, our V1, our T1, or T2, sorry, and then divide by P2 times T1. And when we do that, we will get 39.5 liters, and we're going to round to 3 significant digits because our original 3 numbers here have 3 significant digits. So that's the combined gas law. So next time we have 2 laws left. One is Dalton's law of partial pressures, and then our very last one is the ideal gas law. So in our last lecture, we'll go through those.